All right, here we are, back again. Let's see here, where are we? So we got through our loading and analysis. So we've really gotten through the bulk of kind of getting something within the software, something that resembles a structure, that resembles what we're trying to analyze. It's got members, it's got fixity, stability, and it has loads on it. And so at this point, right, you're going to either you're going to have to potentially troubleshoot your model, right, if things aren't working appropriately. And as I mentioned at the end of the last lecture, when it goes through the analysis portion, there's checks and status, and we're going to go through some of that here. So as models grow in size and complexity, so does the chance elements or boundary conditions will be misrepresented. Leading to instability of the model or inaccurate results, right? Which we don't want either of those, right? And so we know, we've talked about this idea of validation. We're going to talk more about that, but when we get to some of these, when you guys get to modeling some of these structures in the real world now, things, there's a reason why we use software, right? Because a lot of what we, used in the past, some of our more hand methods or predetermined, calculations or analysis really doesn't have the depth of capabilities to do some of the structures we're doing today. So, things are going to get complicated. There's going to be a lot to them. There's going to be thousands of members and thousands of plates and potentially thousands of nodes. And so there's really a lot going on. And so luckily, within the software that we have, on the industry side, they do have some support, right? And so there are internal model checks that can point out possible issues. Programs really vary. In their level and type of support. Right? I would definitely say that from my experience, which I know is very limited, VA to me seems to be more of a, like academic style finite element software for structural engineers. It's very, what is the word for this? It's definitely not super black boxy. It has a lot of capabilities, but I'd say that those capabilities are a bit more challenging to implement in VA, sometimes relative to some of the other software packages. As I mentioned before, RAM is another one that I've had some limited experience with. And if you did RAM structure, they are super tailored to steel and concrete on metal deck buildings. And so a lot of the things are super automated or are very tailored to a specific application. And so when they do that, they are very good at doing one thing. And so, depending on our software we get, they're going to vary in how much help they can provide us as a designer as we go through the design process. They all have, obviously, as everything does, help files and videos. I showed you where to get some of the videos for IES. You can get those out on YouTube. I bookmark the help file for VA because it is very robust, and it does describe a lot of what they're doing. And so I suggest checking out those. So help files and videos with modeling topics, right? Going through example projects or aspects of whether you're designing from the analysis or you're modeling to hopefully get analysis results. So some items to watch for from software is in VA, they provide a statics check. I mentioned this in the last lecture briefly. So, your applied loads. And specifically, what happens is they provide the applied loads on the deformed geometry while looking at reactions of the undeformed, it's got to be right, geometry. So provide applied loads on deformed geometry while looking at reactions from undeformed geometry. It's essentially quantifying, is your load path sufficient? Does equilibrium make sense? Do we have large displacements or relatively small displacements, right? When we've derived all of our elements, right, we made this assumption that our displacements were small enough that we could conduct equilibrium on the undeformed geometry. And so what this does is kind of highlight some of that, saying, hey, by the way, maybe your displacements are kind of excessive because your statics don't work out, right? Because your geometry deforms quite a bit. So as I mentioned, this provides a feel for displacements. Right? Not necessarily a direct indicator of instability or an issue. Right? This is probably one of them, I wouldn't say the most common, but it can sometimes be one of those times where we get a yellow kind of cautionary warning in the analysis tab from VA. It says, hey, by the way, your statics imbalance. There's an imbalance in your statics, and they give it to you in a relative percentage. There's definitely been plenty of times where they have said that warning, but in reviewing the displacements and the behavior of my model, I still feel confident in what the results are, and I use those results. So it doesn't always end up as an indicator that there's a significant problem, right? Because we are always, we are modeling based on small displacements. And so what it's telling us is, hey, if your displacements are excessive, there might be some issues in the overall kind of underlying derivation of the elements we're using. And it could lead to inaccuracies. All right, let's see what else we got. Member stresses. All right. Member stresses. VA, as do other programs, but VA definitely does member stress analysis where they'll look at and say, okay, we have created this model, we have all these elements in there, these elements have have been deemed some profile, right? It gives us geometry for them, but also we've designated materials, and so those materials give yield ultimate stresses, right? And so it can then go through and figure out in post-processing the stresses, right, that are in our elements, and they could say, oh, hey, by the way, this W16 by 26, it has exceeded its yield stress, right? And one of the other assumptions we've made in our derivations, we get through our, when we went to the principle of total stationary potential energy, we made this assumption that we have a linear elastic, right? The internal strain energy was 1/2, stress times strain. And so we, made this distinction that we weren't going to go beyond yield. And so if some of our member elements do go beyond yield, that could be a potential problem, right? That may or may not be a problem though, right? I mean, you may be looking to, maybe your analysis is just trying to come up with results, i.e., you want to analyze a continuous beam, maybe a 4 or 5 span continuous beam, and you put a W16 by 26 in there. Yeah, potentially you could go beyond the material stresses, but that might not be the case if you impose a W24 by 68, right? But in order to get the results you want, that doesn't affect the accuracy of the moment and shear diagram across that 4 or 5 span continuous member, right? But VA, all they can say is, well, hey, by the way, the member you're using, that stress is exceeded, and there might be a problem. So they can say if stress exceeds material yield. Again, as I mentioned, with our 4 span continuous beam, it's not necessarily a direct indicator of a model issue. Right? And overall, the reason why they're bringing this to us, or indicating, hey, we're beyond yield, is that if we happen to say we wanted to use a W16 by 26, we're going to go beyond the yield plateau, and our strain energy is not the same. So the derivation for our elements are not accurate. So it's not an accurate representation. So modeling is based on linear elastic behavior. Oh man, back's killing me. So, another thing VA can do, right? Well, it knows all the nodes that you, develop for your model. It knows what type of fixity we impose upon those nodes, right? Node fixity. And really, it can tell if there are 0 stiffness terms. Right? So models can tell if our model has the potential for rigid body modes. Right? If every node within your model has the ability to translate in a given direction, well, now all of a sudden we have the ability for an entire model to move, right? It's unrestrained. Models can also tell if the node is not connected. To anything. And this comes up a lot, or has come up a lot for me when you do the Revit link, the VA to Revit link, kind of VA Revit link add-on they have. And so they can, when you try and take the Revit model and you push it into VA, as I've mentioned before, there's this analytical model that is not necessarily the model we see in Revit. You can show it, you can have Revit show it to you, but it's really showing you the center line of each of your members. And we've talked about how, well, at a floor level, you have all these different size beams. Well, the center line of all those beams are at different heights, but Revit, is trying to give you every single one of those. So when you put it into VA, now all of a sudden you got these nodes that might be separated by fractions of an inch. And so depending on how that process, works between Revit and VA, you can get these nodes that get developed that can be not connected to anything else. And so VA will know that. It'll say, node blah, blah, blah isn't connected. So, node fixated, this information will help get the model going, but might be stable yet not represent the mathematical model, right? And so, it's going to tell us, hey, you have this potential for rigid body modes. You have nodes that aren't connected to anything, right? These are all valuable aspects of, I guess, troubleshooting your model. But in the end, you don't just have to go through and get rid of all these warnings, right? They're there to help us, but it's not necessarily going to guide us directly to the way we want to analyze or model a structure. So we'll help get model going, but might be stable yet not represent mathematical model. Right? You just want to go through here and just make it so that you don't have any warnings. That is not the case. We want to make sure that we are spending the time and doing our due diligence to make sure in the end we're trying to represent our mathematical model, right? And ultimately representing in connection with our mathematical model, the real world. Our software packages provide us with our displacement. So those packages can then evaluate that displacement and their relative magnitudes. Right? And really they're saying, what we're getting here, is it reasonable? Right? So our light years help email that Adam got, right? There was a warning that talked about the displacement magnitudes, right? And so when they say relative magnitudes, VA says, all right, if I'm designing the Golden Gate Bridge, for instance, right? And you model it in VA, the displacement at this mid-span of the bridge could be relatively significant, right? Feet of displacement probably. And if that thing deflects in a magnitude of feet, right, that's not necessarily a concern to us because we're looking at a span that is, thousands of feet long. And so our relative span to displacement ratio seems reasonable, right? So VA knows the extent of your model. And so it really does. It looks at the extent of our model in a given direction. And then from that, it will discern, okay, well, hey, we have a beam spanning 30 feet and we get a foot of displacement, right? That's a pretty significant amount relative to a 2-foot displacement out of the Golden Gate Bridge. So programs can assess level of displacement and warn of concern. Right? Again, they're not saying, hey, there's something messed up. They're just saying, hey, this seems a bit out of the ordinary. And they just give you a heads up to say, hey, you might want to evaluate this a little bit more. All right. So those are some of the built-in methods that can be utilized by a software package, and I'm sure there's other ones depending. Those are the main ones that I think are definitely valuable, especially relative to VA. And I'm sure there's other ones in other programs. Some of these other ones kind of experience methods relative to troubleshooting here. So, over time, you will begin to develop your own techniques and processes for modeling and working through problems in analysis. I know some people that like to use Excel and maybe in RISA, that's the only option you have, is utilizing Excel to input all of your nodes. I know some people use AutoCAD relative to VA because it can import DXF files to develop their model. And so I'm not saying that there isn't like a one size fits all or one method is the best for modeling. It's another one of those engineering things where there's a million right answers. I'll just tell you that it will take time. And for some of you that do have some experience interning, I'm sure you have all experienced this, that, at this point, you feel probably a lot more confident in modeling than you did when you first started out, right? I mean, it's kind of like drinking from a fire hose. And I'll say it will take time. Hours, days, and honestly, years. I'll also say that it's one of those things where if you don't use it, you lose it, right? I mean, I really enjoy the teaching aspect of what I'm doing now, but at the same time, there are definitely aspects of design that I haven't been engaged in a while, and so I'm not as excited about, say, maybe doing something of those, a design of like that, just because I haven't been doing it recently, right? And there's a lot of things, and that happens as a full-time designer. I mean, there were times where I went a year or two without doing any wood design because I was doing a lot of steel and concrete, right? And so you get this comfort level with different materials. You potentially get comfort with certain software packages, and so it will happen where you kind of get in your own methods and what works for you, and that's fine, because overall you've got to feel confident in doing this, and that's another reason why your model description is so important, right? Because you may have gone about modeling something a little bit differently than someone else, right? Your lines of symmetry might be different. We talked about symmetry in design. So you might have come at something a little bit differently. So it's good to have some description as to how you did that. So experience will come. I guess one of the big things that I've learned is that, there's always pressure. And I remember being an intern, there's pressure to perform. You want to exceed expectations. You want to do things faster than that anyone's expecting you to. And so you're kind of in this rush mode. And so I would say that, one, and now that I'm beyond that, I never ever have the expectation for anyone just starting out to just absolutely crush it. You're going to spin your wheels, and that's valuable time spent at the beginning of your career. Is spinning your wheels, because it gives you this kind of foundation to better set you up down the road, right? Creating these techniques and maybe diving into things a little bit deeper at the beginning, so that you kind of have this more deeper understanding. Maybe at some level you create checklists or procedures for different designs. Maybe you create MATLAB files, like Jake and Will, or MathCAD files, so that you can develop a nice process for doing things, the second and third and fourth and fifth time. And so instead of, being in a rush and being in a hurry, I would say try and be systematic and not reactive. Try to be systematic and not reactive. Right? Don't just, look at those, what do you call them, the warnings, and say, okay, node such and such is free, or node, whatever, 5 or 6 nodes are free, and you go out there and you fix them completely and you go to run it again. right? I mean, be systematic. Make sure, okay, well, if those are free, is there anything else that's free? Why were those free in the first place? Were they nodes that I developed on accident, right? So just be systematic and not reactive. So don't just chase program provided errors. As there can be many. Or misleading. Adam Stordahl talks about when he came in talking about VA, is one of the methods that VA uses to try and guide the designer to a source of instability is they go through and they analyze the natural frequencies of a structure, and they go through and they give you some of the least the lowest frequency modes, and so I honestly I feel like it's very limited the benefit that I've gotten out of chasing down those modes. You can depict the modes in your results case and animate them if you want. But I really feel like those are fairly limited in their value. And VA is pretty limited in its ability to say, hey, you need to do this, this, and this, right? It has no idea what we're modeling as a designer. So don't just chase the provided program errors, as they can be many of them, and they can be misleading. You got to kind of be systematic, right? I would say start with nodes. Right? And be systematic, right? So you can do top down, right? Or end to end of your model, right? And reevaluate boundary conditions on those nodes, locations of those nodes, whether those nodes are attached to anything. I'd say one of the biggest things, I'll make a note down here, is that the find tool and I'd say cut planes are very helpful. And I would say that other programs probably have similar abilities where it's really just allowing you to adjust the visibility of elements within the model to make things a little bit more manageable, right? If you had Cobley Hall and you were modeling it and you wanted to then evaluate all the nodes, it's nice to just say, okay, let's just look at the roof, right? Ignore all the other elements, like hide all the other elements in my model. Let's just look at the roof, right? And then systematically work your way down from the top down, or from one end of a bridge to the other, or something like that. Start with nodes, and then, because when I am developing a model, I start by modeling nodes for a big structure, right? You can establish those nodes at grid intersections and things like that, and then you can step to the members. Members, same thing, right? Top down, end to end. In members, there's a bit more to members, right? Members have geometric properties, they have material properties, right? You can also dictate what a member, whether it is a column, so a vertical element, a horizontal element, a beam, or a diagonal element, a brace. And those designations have implications or I guess, ramifications in VA relative to how load is distributed. I'll let you guys dig into that whenever you get to it. But in the modeling tab, in the project manager, I think modeling, if you clicked on a member, you can dictate whether it's a column, a beam, or a brace. And what that does is it helps VA establish limit states that it looks at. It also allows it to determine how areas are going to distribute loads. So areas don't distribute to bracing. So if you had, say, a main wall, and you decide to draw an area on the end of a building, maybe it's the gable end of a residence, right, single-family home, and you put a wind load pressure on it, and all of a sudden you've got bracing in that wall. It doesn't load the bracing with the lateral pressure. It just loads beams and columns, right? Which makes sense that it would. And so you got to think about sizes, right? Geometric parameters, type, joist, girder, moment frame, right? What is this member doing? You could also say material. Right? We wanted to get rid of some of the errors relative to yield stress and things like that. One thing I would say is that, that yield stress, material stress warning can play a role in the structure if we're thinking about stiffnesses, right? So if you decided that you modeled a 4-span continuous beam with a 2x4, it's going to say, hey, you've exceeded the stress of a Doug fir, and then you say, well, I'm going to model it as steel, right? You're going to get the same results there because the stiffness is consistent throughout the continuous beam. But if you had 2 different beams, right, now all of a sudden it does play a role as to the stiffness, right? And so you just have to be careful about that a little bit, making sure that you don't have an influence of stiffness that's going to dictate, how steep is that line in our stress-strain diagram that gives us our strain energy, right? Are we going to change the amount of strain energy? Then lastly, I do plates. So plates, again, top down, end to end. Right, thickness is important, type, etc. Right? Is it membrane, things like that. And as I mentioned, the fine tool and cut planes are very helpful because you can isolate the elements in your model, which make, again, easy to be systematic, which is key. If the model still isn't running, right, after you've done all those things, there's some steps that I've taken to try and kind of isolate things, right? The first one you can do is fix all the nodes. That's all 6 degrees of freedom, setting them to 0. Right? What will this do? Well, it will highlight a node issue or element issue. We want to make sure, we're systematic. So, if we fix all the nodes and all of a sudden our problems go away and our model runs, well, all of a sudden we know that that stiffness that we've now provided affected the overall, ability for VA to analyze, invert the stiffness matrix. And so once we do that, though, right, we have to be systematic in taking it off. So now all of a sudden you fix all these nodes. Well, now maybe we start at the bottom and work our way up, or top down, whatever it is. And we look at, okay, let's look at all the roof nodes. Let's now release the roof nodes. Do we have that instability or do we not, right? And at some point, that stability will show up and we can hopefully hone in on what the root of the problem was. We can remove all member releases. Right? Again, this will highlight we'll highlight a member release issue. Okay. Next, we've got nodes, members, plates. We can remove all plate releases. Right. Again, this highlights if it's a release issue. One thing with plates is this, as I mentioned, you can dictate whether it's membrane or thick plate behavior. So we can remove any membrane action, right? If it's a membrane only plate, it doesn't have any stiffness out of plane, which can be funky if it depends on how we apply our loads. So we have to be careful about that. So we can remove any membrane action. This highlights an out of plane issue. Okay. And all of these, right? I mean, you could do, there's not necessarily in this exact order, but we can do this in steps. And that is my biggest recommendation there, is to do all of this in steps, right? Be systematic, i.e. sometimes you might not want to fix the entire, remove all the member releases in the entire building. Maybe you do one floor or one diaphragm, right? At a time. Just be systematic, because at some point you're gonna get over a threshold where now all of a sudden the model's going to run. And lastly, if the model still isn't running, this is when we start to simplify. We want to simplify the model. We want to remove, remove degrees of freedom. Or finally, maybe you need to change jobs. It's funny. Right? And you'll feel like wanting to change jobs sometimes, I guarantee it, as you get to some of these complex models, right? And so, when you think about simplifying the model, maybe you break off one bay, or you start by looking at one floor, and simplify things. We're going to talk about validation here, but it's important that we understand fundamentally, or have an idea of what the behavior of the structure is going to be, based on our analysis, right? And so we can do that by simplifying the model and making sure that it meets kind of our gut check, right? And sometimes just meeting some of our kind of rudimentary sort of validation techniques, looking at statics, looking at display shapes, things like that. So anyway, it's not all pain, but sometimes it can be painful to get these models running. There's, like I said, thousands of members and thousands of plates. I mean, there's times where it definitely took me a week or potentially more to get a model running efficiently and getting results that I feel confident in. And then at the same time, the architect, 2 weeks after that could come back and say they want to move something. And then it changes everything, right? It changes all of our analysis. So with that, I'll stop there. That concludes our lectures for this week. And as of right now, it's looking good. I'll make an announcement on Sunday, but I still feel like I'm at a point where I should be able to face you guys in person and not collapse. So if you have any questions, give me a shout. And